So in the first video we did on magnetism, it was mostly like how do we visualize a magnetic field, and we saw that it was very similar to the way that we would visualize an electric field. So today what we're going to do is start figuring out how can we calculate some values, how can we figure out how strong a magnetic field would be at a certain point, or what force would it have on some kind of charge more specifically. So the bulk of questions that you'll run into just deal with the relationship between magnetic fields and moving charges. So usually you'll be predicting which way a charge is going to go. So all of a sudden there's a force. How is it going to affect the path of some charge that's moving through a field? Or if you wanted to move a charge a certain way, what kind of magnetic field would be responsible for that? So how do we calculate magnetic force? A magnetic field exerts a force only on moving charges. So if we have some magnetic field and we're going to use a capital B for some reason to represent the magnetic field, and we have a charge Q that's moving with velocity V, then we can figure out what the force is on the charge by using this equation. F equals Q times the quantity V cross B. Alright, so this operation right here between V and B is called a cross product because velocity is a vector and the magnetic field would be a vector. We take some cross product between the two. Essentially, it's a way that you can multiply two vectors and get another vector out because we want force to also be a vector. Since we're AP Physics 2 is just an algebra-based class, you won't have to worry too much about cross products. If there's ever an angle, we'll look at that case in a little bit. So you won't have to worry about actually being able to figure out what a cross product is. That would be later on if you plan on taking some higher up math or science courses. Magnetic field strength, when you do Q V cross B, or sorry, that would be the force. The magnetic field, just the B magnetic field, is measured in Teslas. You can shorten that to capital T. So 1 Tesla is going to be equal to, well, if we solve this for B, we would have newtons divided by coulombs times meters per second. Let's work that out. So 1 Newton per coulomb times meters per second. If we simplify the denominator a little bit, we have coulombs over seconds, which we know is an ampere. So we could simplify this a little bit further down to 1 Newton per ampere times meter. Put that in parentheses. So 1 Newton per ampere meter is a Tesla. So I said just a little bit ago that this relationship is actually called a cross product. So we take two vectors, we get a vector out. The only trick is they all have to be kind of perpendicular to each other. They all have to meet at right angles to each other. So we can actually do that pretty simply. We can figure out the direction of the V cross B part by using what's called a right hand rule. So make sure you're taking your right hand. So step 1, make sure you're looking at your right hand. I even do it sometimes when I'm writing with my right hand. I'll try and apply these rules with my left hand, and you get a wrong answer. So it's really important that you're using your right hand. All right, next step, take your index finger of your right hand, and that's going to point in the direction of the velocity. Points in the direction of the velocity. So index finger points in the direction of V. Next step, your middle finger will point in the direction of the magnetic field. So middle finger points in the direction of the magnetic field. And then last step, if you take your thumb and point it perpendicular to the other two, kind of like you're giving someone a thumbs up, that will point in the direction of the force. Thumb points in the direction of the force. So keep in mind that figuring out the direction of the force this way only accounts for the V cross B part. Don't forget we have that scalar Q out front, so the amount of charge will have an effect. So if Q has a negative value, then our overall QV cross B will have a negative value. And that's going to force the vector to actually point in the opposite direction. So when you do these right-hand rules, it kind of sets it up for a positive charge. So if Q is negative, you just have to flip it in the other direction. So if QV cross B is a negative value, so Q was negative, the force vector will point in the opposite direction from your thumb. So you do your right-hand rule. If your thumb points at you, but Q is negative, it should actually be pointing away from you. So you can always figure out how big the magnetic force is without doing the right-hand rule. And this is where it gets a little bit simpler if we know an angle that is between our velocity vector and our magnetic field vector. Then we can simplify the equation down to F equals QVB times sine theta. So the sine theta part actually removes the cross product for us if we know what the angle is between the two. So the sine theta term is actually pretty helpful here because we could see right from that if the charged particle is moving in the same direction that the magnetic field moves, then we know that theta would be 0. They're in the same direction, so there's no angle between them. So sine of 0 would give us a 0. The total overall force would end up being 0. We have Q times whatever V times whatever B times 0 all lines up to be 0. So sine theta term is important because we could see very quickly that there is no force when V and B are in the same direction. So no force when V and B are in the same direction. We can also tell from the sine theta term when we'll have our highest force, the maximum possible force. So maximum F occurs when V and B are at right angles to each other, so 90 degrees. So when they're perpendicular, you'll have the highest possible magnetic force. Alright, quick example. We have a charge, this little dot right here, of 5 coulombs that moves upward towards the top of the page at 2 meters per second, and it's in a magnetic field of 0.3 Tesla that points down into the page. So we're starting to add a third dimension here. So what is the magnitude and direction of the force that the charge is going to experience? So we can figure out magnitude really easily. F equals QVB sine theta. So what's our Q? 5 coulombs. Our V, 2 meters per second. Our B is 0.3 Tesla. And then sine, what's our angle? If this is up the page, the magnetic field goes into the page, they'll meet at 90 degrees. So 5 times 2 is 10, times 0.3 is 3, times 1 would get us a 3 Newton force. So magnitude, not too bad. Just take all the numbers you know and plug them in. The tricky part here is going to be figuring out the direction. So first time we're trying to apply our right hand rule. So remember, index finger of your right hand points in the same direction as V. So take your index finger and point it straight up towards the top of the page. Then remember, your middle finger will point in the same direction as the magnetic field. So take your middle finger, make sure you keep your index finger pointing up with V. Your middle finger points into your computer screen or into the paper that you're writing on, so it goes with the magnetic field. Then, if you have your thumb sticking out like you're giving someone a thumbs up, you can see that it should be pointing off to the left side of the page. Since we have a positive charge, we don't have to worry about flipping it. Our Q is positive, so it keeps our force positive. So the direction would be to the left. So what is magnitude and direction of the force that the charge experiences? 3 newtons to the left. So this is kind of something new, maybe completely new for some of us. We haven't done really anything in 3 dimensions prior to this, and it's probably not something that you likely ran into a lot of anywhere else working in a 3-dimensional space. So just a quick little note here. The magnetic field lines that we had in this example that go into the page, we represent that with circles with an X inside of it. So anytime you see a circle with an X inside of it, that means it's something that goes into the page. If you have a vector that points out of the page, that's just a circle with a dot inside. So you either have a circle with an X or a circle with the dot. One way that might help you keep that straight is to think about them as an arrow. So if you're looking at an arrow coming towards you, you would see just the tip of it. It would look like a little dot. If you looked at an arrow that was moving away from you, you would see the feathers, the fletching. I don't know what kind of arrows these people are talking about. Most arrows I know only have 3 feathers, but whatever, I guess it works. So from the force equation that we had in the previous page, the direction of the force, we can see, depends on the direction that the particle is moving in. So really big factor in determining which way the force will be exerted on this particle. But since you're applying a force, you're changing the velocity. As you change the velocity, you change the direction. So the overall size of the velocity doesn't change. Since you're always applying the force at a right angle to the velocity, it can't get any faster. None of the force will make it speed up. The force is only going to change its direction. So we always keep the same speed, it just is constantly moving in a different direction. So in the example that we saw above, that 3 Newton force was pulling the particle to the left. But once the particle starts to move a little bit, if it's getting pushed to the left, it changes its velocity. So its velocity is no longer straight up, Now it's somewhere up and to the left. So since we have a new velocity, we have a new force. So as long as a particle's velocity vector is always at a right angle to the magnetic field lines, then the force will always be at right angles to both of them. So if you have a force that's always perpendicular to velocity, I'm not sure how much you remember last year from circular motion, but that's kind of what we have going on here. So it's always, the force is always pulling in towards the middle here of this circular path it would kind of trace out. If we kept going here, it would come right back around to where it started. That's a pretty awful picture. The force should be pointed towards the center of the circle. I don't know. I don't know what happened there. A force that always acts perpendicular to the velocity of an object causes circular motion. So because velocity vector and magnetic field lines are at right angles to each other in that example we looked at earlier, the magnitude of the magnetic force was just F equals QVB. Our sine theta term turned out to be 1. And also, this will be a stretch if you weren't in AP1 because we didn't really talk about circular motion in college prep physics. Heck, it might even be a stretch for AP1. That was a long time ago. We have an equation for centripetal force, force that causes things to move in circular motion. So this is an equation from mechanics, mv squared divided by r for centripetal force. If we combine these two things, since in this case they're the same thing, we can solve for r to figure out how big of a circle we'll have. So it would initially look like QVB is equal to mv squared divided by r. If we want to solve for r, then we could say that r equals mv divided by qb. So v squared on top and 1v over here would cancel out. So r is mv over qb. So if you know all this stuff on the right hand side, you can figure out just how big of a circle it would make. So that stuff we've been working with where they're perpendicular, that's probably the second easiest case of a charged particle moving through a magnetic field. Easiest case would be when the v and b vectors are parallel. So magnetic force acting on a moving charged particle is cross product. So if they're parallel to each other, we'd have sine is 0, it makes the whole thing 0. So easiest case, if you have a velocity in the same direction as a magnetic field, there can't be any force associated there. So right off the bat, you know it's going to be 0. That's why that's the easiest case. So now we come to this in-between stuff. Not like it's really difficult. You just add one little extra thing to multiply. So they're not perpendicular and they're not parallel. So easiest way to deal with this stuff is to break it up into components. So you'll essentially break it up into part that's parallel, so 0, and a part that's perpendicular, which is like the stuff we did in the example problem. So if we look at this example here, we have our velocity, it moves up and to the left, so we take the x component of its velocity, and we have the y component of its velocity. So x component of the velocity, where'd my typers go? So the x component is perpendicular now to the magnetic field. So the x component will move in circular motion because it's perpendicular to the magnetic field. So if we apply the right hand rule to that, well, then we take index finger of our right hand, point it to the left. Take the middle finger, point it up towards the top of the page. So if you're doing it the right way, your palm should be facing up. That's the easiest way, maybe the only way. I don't know. I'm not that flexible. Your thumb should be pointed right into the page. So we'll assume here our charge is positive. So assuming the charge is positive, the force is directed into the page. Okay. If we look at the y part now, the y part points up. B also points up. That means they're parallel to each other. So the y part is going to experience no force. No force, no acceleration. And that's because our two vectors are parallel. So as a result, what is going to happen to that particle? So our vertical component, it doesn't just go away. It just doesn't change. So it's always moving upwards. But in the x direction, it's moving in a circle. So what will that cause overall? I'll do it over here. So we start out right here, and we know that initially our force is directed down, so we'd be going into the page. So we start out here, we go down into the page, come up out of the page, down into the page, and up out of the page. All the whole time we're still moving up. We're just making a horizontal circle while we're moving up the whole time. It ends up looking maybe not like this, but a little more like a helix. So as a result of this combination of force and no force, I guess, the particle moves in a helix-shaped path. Horizontal circles and straight line vertical, I guess, if we want to try to throw some describing words in there. So as a result, trajectory, let me get a picture of that. Alright, so a little bit better than what I did. Just keep in mind that it's down into the page on the right side, up out of the page on the left. Down, up, down, up, down, up. Okay, so here's where we start to differentiate. So if we have a positive charge, it moves so down here, up here, down here, up here. If you kind of think about these circles as a clock, it would be going in the same direction, so it would be moving clockwise and up. If it has a negative charge, well, the vertical part doesn't change at all. It still follows the same path. It's just that instead of going down, up, we go up, down, up, down. So a negative charge would just be in the opposite direction, so counterclockwise and up. Alright, example of this. So we have a particle with a mass of 1 times 10 to the minus 5 kilograms and a charge of negative 10 coulombs. It's moving in a clockwise circular pattern of radius 2 meters at a speed of 1 times 10 to the 3 meters per second. We want to figure out what is the magnitude and the direction of the magnetic field that's acting upon it. Whew, all right. So we had that equation we set up where we talked about centripetal force being the same as magnetic force. So we had QVB equals m v squared divided by r. So since we want to solve for b, we could rearrange this equation to look like b equals mv divided by qr. So with the numbers that we have, 1 times 10 to the minus 5 kilograms. The speed is 1 times 10 to the 3 meters per second. Close. And then we divide that by Q is negative 10 coulombs and R is 2 meters. So we have 0.01 divided by 10 divided by 2. 5 Teslas. So 5 times 10 to the minus 4 Teslas. This, though, is only half of our answer. We got the magnitude. Now we have to figure out what is the direction. Alright, so to figure out the direction here, the way that this picture is set up, we have the velocity initially pointing up. If it's moving in a circular path, then we know the force has to be towards the middle. So remember, index finger is velocity. That one should be pointing straight up towards the top of the page. Thumb is for force, so that one should be pointing in towards the center of the circle, so off to the right if we're at this point here. And then stick your middle finger out so it's perpendicular to the other two, and you should be pointing right at yourself. So the answer here, we would say something like 5 times 10 to the minus 4 Teslas directed out of the page. Careful of, though, is that this time we're dealing with a negative charge. Remember, negative charge flips your right hand rule around. So if you did the right hand rule the right way, you're pointing at yourself. But since we have a negative charge, we have to change that. So it actually points into the page, only because we're dealing with a negative charge. If we had a positive charge, it would have been out of the page. There's one more example in this section about magnetic fields and electric fields overlapping, but I think we will save that for next time and focus for right now just on being able to calculate and determine directions of forces due to charges in just a magnetic field. So we'll save that one for next time.